This is slide number 13 and I am your presenter Asloob Mudassar. From the previous slide we have found that the vector propagation vector k is perpendicular to the vector joining the point P not to P. So the product the dot product should be 0. So we have written k dot P not to P is equal to 0. So substituting the values of k, which is equal to kx iota into unit vector I plus ky into unit vector j plus kz into unit vector k, and substituting the value of the vector p not p from the previous slide and evaluating the dot product, we get this expression, that is k cos of alpha into x minus x naught plus k cos of beta into y minus y naught plus k cos of gamma into z minus z naught is equal to 0. Now substituting the value of k is equal to 2 pi over lambda and taking the x, y and z coefficient on the left hand side and x naught, y naught and z coefficients on the right hand side, we have the following expressions. Now you see that on the right hand side of this one we have 2 pi constant, cos alpha over lambda constant, x naught constant, and similarly cos beta over lambda constant, y naught constant, cos gamma over lambda and z naught are constant. So the right hand side is a constant. That's why we can write constant, that the right hand side is equal to constant. And we are introducing new variables, that is fx is equal to cos alpha over lambda, fy is equal to cos beta over lambda, fz is equal to cos gamma over lambda. Substituting these one on the left hand side of the above equation, we get 2 pi into fxx plus fy into y plus fz into z is equal to constant. So this value is a constant, you know. We shall be using fx, fy and fz repeatedly in our course on Fourier optics, especially when we are evaluating the Fourier transform of some quantities. There we shall explain their physical meanings also, but at the moment you just remember that these are related with the direction cosines of the vector k, of the propagation vector k of the wave. So we have this expression 2 pi into fx plus fx into x plus fy into y plus fz into z. The product is equal to constant, and then you see that we can write, whenever we want to write any plane wave, we can use either sine of this quantity, that is a sine of 2 pi of fx into x plus fy into y plus fz into z, or we can use the cosine function, that is cos of 2 pi into fx x plus fy y plus fz into z. So plotting these two functions, we can plot actually the plane wave traveling the plane wave. So this will give you the profile of the plane waves, that is the plane waves can be the profile can be obtained using the sine function or using the cosine function with the argument as we have given. And you know that this argument, which we refer to as the phase factor, is constant as we have stated earlier. Now when we are writing the plane wave in the sine form or the cosine function form, their mathematical manipulations is not simple but very difficult. For example, if you have two functions, sine of something divided by sine of something, and arguments are not the same, then you know that the division is very complicated. But with exponential representation, the mathematical manipulations are very simple. So we can write the mathematical manipulations of the sine cosine function or the cosine function in terms of the exponential as given: e to the power iota 2 pi into fx x plus fy y plus fz into z, and separating the z component separately and writing the other two components, that is e to the power iota 2 pi into fx x plus fy y. And you know that we have approximated on the rightmost, we have dropped the constant factor, which is e to the power 2 pi fzz, because z is a constant and the propagation vector has a fixed direction. So e to the power iota 2 pi into fz into z, this may be regarded as the constant phase factor of the plane wave, and for a given value of z, that is for a fixed value of z, this constant is fixed and we can drop it, because physically this constant will not matter if we drop it. So we have the final expression of the wave is e to the power iota 2 pi into fx into x plus fy into y. But remember that whenever we are writing any real component into the exponential form, just for the sake of mathematical simplifications, we must remember that we we are considering actually the real part of this quantity, that is the real part of this exponential quantity. Remember that if we expand e to the power iota 2 pi into something, that will be equal to cos of 2 pi into something plus iota into sine of 2 pi something. So the arguments will repeat with these two. So if we consider the real part of this one, we shall get cos of 2 pi into fxx plus fy into y. So the phase factor e to the power iota 2 pi fzz is constant at a plane, that is for a given value of z it is constant and has no physical contribution, and thus it can be ignored. So here we end the slide number 13 of this course.